So last time I introduced the concept of what is called a superoperator evolution, and today I am going to discuss various consequences which follow from that. So this also goes under the name of Kraus representation because it was worked out by Kraus. So the first step was the explicit construction of a Schmidt decomposition, which said that any density matrix, I can always expand the system to construct a pure state without any loss of generality. What the superoperator does is perform the evolution of that pure state, the expanded space, and then trace over the unobserved degrees of freedom to find the consequences of one part. And all the axioms of quantum mechanics, which I described earlier for pure states, now come to this reduced description, which is somewhat different, but everything can be converted from the pure state axioms to these reduced state axioms, and that is what the superoperator description allows you to do. So first step was just to expand the space. So where I just wrote down evolution as a psi A cross 0b going to and then when the trace was taken after this evolution of the density matrix, then the density matrix of the state A transformed to with the constraint that mu dagger mu is equal to identity. And these operators were just conveniently defined as the overlap of whatever transformation you perform between 0 and mu. That was a construction which I used. So now this is a generalized version of how a density matrix evolves. Other than this normalization constraint, these things are free. There can be any set of overlap components, and so there is no restriction that mu has to be a unitary, Hermitian, anything like that, nothing. They can be much more general, and so there is a lot of freedom in terms of what are the variables that will parameterize this matrices on mu. Okay. So then I wrote down one result last time, that both unitary evolution and projective measurement are special cases. with only one term, and in this case replacing this mu by a projection operator. Because if there is only one mu, the sum doesn't matter. It becomes some matrix rho A, some matrix conjugate, and with this condition, that matrix is unitary matrix. So that is the first case. And in case of measurement, the projection operators are Hermitian, and p square will become equal to p by definition of a projection operator, and sum over all the projection operators gives identity, the completeness relation, and the transformation is just projection operator times density matrix times a projection operator. So this is something which I mentioned last time, but now we can go further than this, that you can ask what will happen if I perform a projective measurement in this large space. What will it look like in this reduced space? Okay. And that construction is known as another acronym, positive operator valued measure. Projective measurement in the large space. This is the two Hilbert spaces for the two parts, and to reduce it to a smaller space. So there is a definition of what this positive operator valued measure is called. Let me put these capitals everywhere because that is the acronym. So it is defined as a set of operators. They are all positive. They add up to 1, and they satisfy the relation that probability of A is equal to trace of rho times pi A. But beyond that, there is no constraint about orthogonality or the normalization. Normalization, the only normalization condition is this. So this one can write it as a positive operator because they are all positive. You have some diagonal representation where some direction A is chosen with some eigenvalue lambda A, but the various A which appear do not have to be orthogonal. The sum of lambda A because of this condition will add up to 1. And this is useful for obvious reason where the number of operators inside here is larger than the space. It certainly cannot be smaller because otherwise it will not add up to identity. But you can have, say, in two-dimensional space, 3 different operators which add up to 1. They don't have to be orthogonal, so you can point them in 3 vectors in the two-dimensional space in some arbitrary directions and assign them as this positive operator valued measure. So how do we obtain these operators from these original definitions? So we'll try the same logic that this is the transformation in the larger space. It's capable of describing the measurement, projective measurement in the larger space without any problems. So I will do that and then trace out this mu degree of freedom which is not observed. So if I want to calculate probability, I'll keep the notation the same as over there. Some operator mu, which is nothing but take mu as one of the result of some projections which is obtained, and now I calculate what is the probability of that particular term from this particular rule, and after integrating out whatever this mu be, I get an expression like this, m mu psi a dot product with itself. Okay. And this in the language of the density matrix, it is nothing but this result. Okay, because psi a I can take it on the other side and write it as trace, but this is the object which appears. Certainly this matrix is a positive matrix because, well, it's a something time is adjoint. And I can now identify that I can express pi a as this particular combination. Okay. So one can identify that and evolution of this stuff. Here it was mu and mu dagger, but this turns out to be a case where the operator is Hermitian and positive. I can define a square root of it, and so I can replace this more general rule by something of this type where whatever is here, the conjugate is identical. Okay. And this is a generalization of what we did with the projective measurement over here, which is where the term the transformation was just this. Now it is this, and here actually I need to write the summation. So this is a very interesting outcome that I can extend the concept of measurement to what is this positive operator valued measure, and there is nothing which is lost. The orthogonality doesn't have to be true. I can define many such operators which add up to 1, and I can talk about the probability of each one of them, and the sum of all these probabilities will add up to 1 also. This is sometimes also called generalized measurement, where the and it turns out that this is also the most expanded version that is allowed in quantum theory, that you want to talk about some directions of measurement and some probabilities. The only thing you need is to add up to 1. They don't have to be necessarily all orthogonal mechanisms, and so and that is proved by a theorem of Neumark. I will just state it. I am not going to worry about constructing it explicitly, but it is essentially done by explicit construction. What the converse says that any POVM defined by these rules can be converted into orthogonal projective measurement in the larger space. So these are all statements all connected with the nature of this one-to-one map, which essentially started with a Schmidt decomposition proof that yes, you can do it one way, the converse also can be done. So this is now complete. If you want to find a representation, say in a finite dimensional space, I mentioned a little before that in t-dimensional space you can have 3 vectors satisfying this kind of condition. Now if you add a third component, then the 3-dimensional space is always possible to make these 3 vectors orthogonal. What I add as a third component is at my own choice, but by adding suitable extra contribution, you can make them orthogonal. And one need to do some simple exercise to convince yourself that yes, this can always be done, but it is indeed so. So that is, well, I will leave it as an exercise, but this is one consequence, rather straightforward enough, of what happens to the case of measurement. I am going through the list of axioms of quantum mechanics. Whatever we discussed earlier, there was measurement, there was expectation values, and then there was the evolution, unitary evolution. It all gets projected in different senses, and I am just going to discuss them in some order. Okay. So let me move on to the next thing. This is this representation it's always been this mu b was just some vector I defined conveniently, and I can apply a unitary transform to it, and if this vector was appearing here and I unitarily transformed, I will get some new matrices. They will satisfy all the same property. In particular, if you do this, then with all these conjugates, UB dagger and UB will just cancel out. A normalization is maintained. So it's not unique. You can have your own choice about what operators you can choose. But what is limited is the number of operators. There is an upper limit. So how many of such operators I can choose? Well, I just have to count various possibilities. It's going to transform something on the A space and something on the B space. Other than that, there is no restriction. The only restriction is the normalization. So the general counting basically gives this upper bound, and this is just to saying any matrix which is normalized, how many components it will have. It's an n-dimensional matrix, so n times n will give the square. The only constraint is this trace is, or this particular condition will remove one component and everything else will just be unrestricted, whatever you transform on one component and whatever you transform on the other component. So that is much more general. So for a qubit, we saw that rho has three parameters. They were the ones given by the Pauli matrices, some coefficient of the Pauli matrices. On the other hand, how many ways you can transform this particular rho has much larger number. This number comes out to be 9. 3 times 3, that is what it essentially becomes. So if you want to write the most general transformation of the density matrix, you will end up with a much larger number of parameters instead of just a unitary transformation which we are dealing with. It had only 3 parameters. So this is something which one can keep in mind, and now it's best to illustrate all this jugglery by an example, because otherwise the things just get lost. They're just generic statements. So what is the example? And for that I will look at something which is used in the procedure for error correction. how do errors occur? There is a system and there is an environment. And some interaction between the two, we don't know what is going on in the environment, and the system's variables change. So I will go back to this structure. This is a system, this is the environment, and this is the result. The environment will change in some way. We have no idea what it is, but we are just going to trace over it. But the system will be modified because some operator is going to act on it. And that is a powerful framework which we will look at in much more general fashion sometime later in the course. But at this point, writing down things which can be done for a qubit is useful enough. Okay. So I will look at only one particular type of example, but let me just what can happen for a qubit. Okay. So in the standard binary algebra, there are only variables are 0 and 1. What is an error? 0 goes to 1 and 1 goes to 0. Nothing else is available. If the bit flips for some reason or the other, we call it an error. Otherwise, it remains whatever it is. Now, this is a more general system because it's a two components, but they are complex components. So you can ask, what can happen in terms of the ket vectors 0 and 1? Well, they can transform again in different ways. One of them is a bit flip, 0 and 1 can still get interchanged, but now there is a complex phase also sitting inside. And the phase can also change. And the three kind of things which you can do. So which are possible to deal with in this particular language. One is called a bit flip, which is state psi goes to the Pauli matrix sigma 1 acting on psi. Remember, Pauli matrix sigma 1 is just 1 and 1 off diagonal. So if I act on this, it will interchange 0 and 1. So that is a bit flip. But now I can immediately write down by analogy what is known as a phase flip, which will be changing the relative sign between 0 and 1. That is actually the phase. And that is represented by this matrix sigma 3. That 0 will remain 0, but 1 will become minus 1.
So it's also one for the global phase or only the local phase?
Global phase is not going to be involved anywhere. The only relative phases which you can talk about. And then, well, since they are written by Pauli matrices, you can have both errors together, which can be written as a second Pauli matrix, but because sigma 2 is nothing but a product of sigma 1 and sigma 3 up to a phase. So these are the things which can occur on a qubit. Now, How many ways they can occur? Well, it depends on the probabilities of how frequent is this, how frequent is that, etc., etc. And you can make a general model, but we will stick to something simple enough, and that is a situation where you construct a transformation where all these three errors are equally likely. Okay. That is a special case. So, and it is known as depolarization. We will see why. And so now I want to describe the situation in this probability language. Some probability the state will remain what it is. Some probability the bit will flip. Some probability the phase will flip. And some probability both of them will flip. Okay. So we can go back to this description. Okay. There are a bunch of operations for the transformation where this matrices mu appear, but now we want the transformation of this particular type, that state should go from psi to sigma 1, and rho will then go to, well, sigma 1 times rho times sigma 1 dagger, but sigma 1 dagger is sigma 1 itself. And so I can assign this structure in this particular formula by the following choice. So there will be an operator where nothing happens, and the square roots are going to appear because of the normalization condition to be clear enough. The probabilities are buried inside here with all these square roots, so that structure is there. So with probability 1 minus p, nothing happens. With M1, it will be bit flip, and I'm going to take all the three equally likely, so I have put p over 3, they will all add up to 1. So this describes the independent possibilities. No error occurs, bit flip, phase flip, and both. All the three are equally likely. I have chosen this 1 minus p structure to automatically satisfy this particular constraint. Okay, here the matrices are such that M is equal to M dagger. So you basically square it. All the Pauli matrices square to identity. And these numbers p by 3, p by 3, p by 3, and 1 minus p will add up to 1. So now we have a description about this kind of errors and the corresponding operators. Let us work out what is this particular result. And that actually is the reason why it is called depolarization. Okay. So, the general state we have for a qubit described on the block sphere is identity plus p dot sigma. Normalization gives this half, where p is a 3-dimensional vector. Okay. And it is also called the polarization because that is the direction in which the measurement will give the value if you try to measure it, and it's also the 3-dimensional vector specifying the state on the block sphere. Okay. You can call it spin, you can call it polarization, whatever it is, it's a generic label. So now I can ask what will happen to this state. So, write the whole thing, well, somewhat of a brute force, but that is fine. There is an identity term which is not going to do anything. So, it will remain I plus p dot sigma with coefficient 1 minus p. Remember, it the square of it is going to appear, and so all these numbers are going to get squared. That's how it was designed. So this is the first term. What is the second term? It is half and then sigma 1 times I plus p dot sigma, sigma 1 times p by 3. Sigma 2 Now let us simplify, collect various terms. The identity part is rather straightforward because it will just commute through everywhere. Sigma 2 square is 1, sigma 1 square is 1, etc., etc. So you put all of them together and this term doesn't change. What happens to this p dot sigma? So p dot sigma has all the three components buried inside it, and when you look at something like that, if there is a sigma 1 component, it will just remain sigma 1 component because this will commute with it and it gets squared and disappears. But if there is a sigma 2 component, there will be anti-commutation. When you take sigma 1 through a square and identity, but there will be a negative sign. And sigma 3, the same thing. So it can be easily seen that in all these three terms, one of the component will have positive sign, the other two will have negative signs. And you just have to combine all those things together. So this is what happens to P dot sigma. And then there is 1 minus P. One contribution will come with a positive sign and two components with negative sign. And that is which you get, and the result is that whatever the length of this vector, it shrinks. And that is why it is called a depolarization. P is the polarization vector. It is reducing in size. And of course, you can go to the extreme case where this number is 0. That means the matrix is just the identity matrix and there is no polarization left. So, you can this is one kind of error, and which is one of the common errors which occurs in real world. You try to make a system nicely polarized in one particular direction, and if you leave it alone, it will just decay down. It will just become random because if the polarization is lost, you will get a matrix which is identity matrix, so there is no direction or information left. Okay. Yeah. What? No, there is a limit how far. I mean, once it goes to 0, then of course there is nothing to go further. Okay. Because whatever this number is, it's a radius vector, and its minimum value is the radius is equal to 0. You do not take this P to be any arbitrary number, it will be bounded. So this is a very simple enough example, but it puts into perspective how all this mathematical formula can be used to define certain kind of transformation. It's a special case, but that is still instructive enough. And there is one more special property which is automatically satisfied by this particular result, that when the reverse of this normalization condition remember, the normalization has this mu, dagger mu, which is a different order than what I am writing over here. And this label is given unital because this is what will happen for a unitary matrix. Both these properties will hold simultaneously. More general cases, this doesn't have to be true. But this has a consequence, and which I am not going to prove any in any general sense, but what is it provides an evolution which is in some sense monotonic. The group theory label is it's called a semi-group. You can move in one direction monotonically, but there is no inverse operation available. Remember, in group theory always there was an inverse operation. The semi-group doesn't allow that, but the physical connection is the one which is more important. What does the monotonic evolution mean? That the entropy of the system monotonically increases. Remember the entropy, we had the definition in terms of the density matrix as I defined earlier, and you can show that under this particular condition, the entropy increases monotonically, and this is the powerful result connected to the second law of thermodynamics. So this property plays an important role about what are the kind of situation which will be consistent with the second law of thermodynamics. You can have otherwise more general evolutions which will not obey this particular rule. And so in those situations you can have transformations where the entropy will decrease also. We most of the time are not interested in those kind of transformations because they are not what you call this monotonically evolving processes. This has important consequences for the macroscopic physics that we want to deal with. So this so-called unital channel plays a role in terms of physical connection. But as I said, all the channels do not have to be unital, and actually you can find implementations of small quantum systems where the channels are not unital and the entropy doesn't increase always. It can go opposite way. There are limits of how much you can do, but there are individual examples where you can do something different.
This channel that we're talking about is the channel which is connecting the two systems. This is channel which is connecting the two systems.
Yeah. When you talk about this entropy and second law, it is system and the rest of the world, whatever it is, the rest of the universe. Then there is this label which I mentioned last time called complete positivity. It is used I just described this as some particular transformation in a spatial constructive way, but if you assume the so-called complete positivity, I am not going to give the proof of this theorem. You can prove that that is the only transformation you can create and nothing else. Okay. So it's again based on the fact that I'm expanding the system to a larger space, and the theorem uses the feature that whatever extension I construct, it still obeys the positivity property. So it uses a particular extension, and that from one system to a larger space, and we have to assume that whatever that extension I constructed by hand obeys this positivity, and the statement of complete positivity guarantees that yes, this is always allowed. But then there is a question that are there any extensions which violate this particular principle? The answer is yes. It will obey all the other properties but not complete positivity. And not too difficult to think of it, but yes, you have to know the very simple map which exists. Which is the density matrix is there, apply transpose on one part and identity on the other part. It obviously has an inverse, which is the same thing. Apply transpose, nothing happens twice. Transpose is such a operation on the matrix, eigenvalues don't change. Okay, you can diagonalize it, transpose of it is the same thing. But you can easily write down a density matrix and perform this operation. And you will find examples where after these particular operations, some of the eigenvalues become negative. What does that signify? So, why that happens is rather trivial. This is a map which squares to 1. So only allowed eigenvalues are +1 and -1. Nothing else. can the -1 eigenvalue occur? And the answer is yes. But what does it tell you where these negative eigenvalues occur? And it means that some assumption which we made in this construction has broken. Okay. And what is that assumption? Well, the assumption was kind of implicit all over the place. It was that of factorization. Yeah, there was A and something you wrote with B, and when the factorization doesn't work, we come back to the situation of entanglement again. So if you take a state and apply this test, if the eigenvalue shows up negative, it's a guarantee that the two components are entangled. Not the other way around. There can be still entangled state which will pass this particular test, but there will be some states for which this result will hold. And one of the simplest example happens to be the 2-qubit Bell states, which I wrote down earlier. We apply this transformation operation and we discover that yes, eigenvalues become negative, and which tells that the Bell states are entangled. We knew it beforehand, but this is just a practical check, and this you can use in many other situations as well, as in some sense test of entanglement. Of course, it's a theoretical test because you don't have any direct way of implementing the transpose map in some practical device. We don't know how to construct the map rho going to rho transpose, but theoretically it's a explicit example, and you can convert it into, with some jugglery, into a test of entanglement. You have to work on it, but in principle, this kind of things are also given another name, like mention it because you probably might see it at some place. It's called entanglement witness. So there are various properties we determine for a system. It is called a witness, and if it shows up in some particular form, you can say that yes, entanglement has been generated. So this is a caveat or a necessity, or why this complete positivity is used in proving this particular theorem, that you are avoiding any of these entanglement kind of scenarios which in principle occur, but then the factorization between the two systems doesn't hold. Because we started with some state which was factorized, and if it is not, then this whole thing is not going to work. And last thing I can says can I convert this evolution into a differential equation form? And it is certainly possible, but it requires extra assumptions. The extra assumptions have to do with being able to construct derivatives. This is a discrete form that some operators are put inside here, but there is no requirement these operators are infinitesimal or anything like that. If we want to construct a differential form, then we have to assume that these operators are infinitesimal. Well, they add up to 1, so one of the operator will be almost like identity, but all the others are small, and then you write it as derivatives. And that assumption that things are smoothly connected to be able to define derivatives requires a condition that yes, things are changing, but they're not changing very fast. That assumption has to be put in by hand, so needs the property which computer scientists refer as Markovian. The system changes, but the change depends only on the previous step and nothing else. In the sense that I can go from the state at t to t plus delta t, and now if I want to go to t plus 2 delta t, whatever is that at t plus delta t is enough. I don't have to go back and look at what is that at psi t also. Because if I have what you call arbitrary connection into the past, then it will not be a differential equation. It will be an integral equation summing over all the past history. Differential equations means that if I have one time, I can go to delta t without referring to anything else. And this has been written in various forms that things depend only on immediate previous step, and various physical ways of saying that information that leaks into environment does not return. If it returns, it will break the Markovian assumption. It's like the examples we looked at before, that an atom is decaying. It emits a photon. But we assume that the photon goes away. If the photon is going to return, which can happen if you put the atom in some cavity, then it will undo the change, and it can happen after a long time, so it will be not Markovian, it will depend on all the past history. And these kind of situations are ignored in this derivation of the differential equation. So you can write different ways that equilibration time scale of the environment is much shorter than the evolution time scale of the system. Something went into environment, the environment will equilibrate, thermalize, whatever it is, and nothing is going to come back from that. The system is evolving, but the system is evolving much slowly. This is another way of saying that whatever went into environment, it doesn't return because the environment is always in equilibrium. If it is not in equilibrium, it can give something back, but it is always assumed to be in equilibrium. So this is a assumption, the computer science description that it is called Markovian. So now I construct a scheme of these operators mu, where I can take a derivative. And so can choose one of the operator will be very close to identity to satisfy the normalization. So I will write it as identity plus some general matrix. There is a implicit notation that there is an arbitrary matrix. I will write it as a something which is Hermitian and something which is anti-Hermitian. It covers everything. But I will only want to keep track of all the objects which are Hermitian. And why this is dt? Because I am going to construct this binary product and there will be all kind of terms, and the term should start at order delta t because I am going to construct the evolution. So because there is an identity in front, there will be cross term which will multiply this with that, etc., etc. And I don't want what you call powers behave anything other than delta t in this particular term. But that is not, so this is M0, the dominant term, and I can then choose the rest of the stuff as some matrix L mu multiplied by square root of delta t. And why the square root? Because it's again the binary structure, two factors are there, and there is no identity combination sitting here. So when you multiply, the result will be of the order of dt. Okay. So this is a reasonable choice, and the meaning of what is over here, etc. will become clear very soon. The first thing is the normalization. So I can construct what is this particular object. And well, I have to, squaring that thing is easy. It is just L mu dagger L mu. But squaring this, well, I have to take the Hermitian conjugate and multiply. So let me just do that. I plus IH plus K well, dt I have to put it in right place. Okay, so now I combine all the powers of delta t which I want. The leading term is just identity, which is the required term, and the rest of the stuff should cancel out. Okay. So this is not too complicated, but I have to basically evaluate what is the delta t order term in this particular combination, and you can see that the delta t terms come from one factor of identity and one factor coming from this IHK. IH and minus IH is going to cancel out, but the K remains. So it is 2K times dt and plus there are higher order terms which I will throw out because this expansion only refer to the lowest order term, and I have to make sure that everything is correct up to order of dt, and then the result is that the choice of this operator k is fixed. Constrained by the normalization. Yeah. Yeah. What row?
Square root dt the first.
Yeah.
Subsequent one gives square root dt for the varied case. Like why did we not take square root dt the first?
In here, because then the cross term will produce a square root of dt term in the expansion. I don't want that. I want to construct a differential equation in powers of dt. I have to construct the terms which go there. So whatever comes out from all the construction, they will all have integer powers of dt and not any other stuff, whatever it is. And now I can write down the equation, because various things are kind of buried inside here, but now I have to take this difference. One of the operator k went away, h is left as it is, unspecified, and I can write down mu rho mu to order dt, and then construct the differential equation. It is not too difficult, so let me. Yeah, so let me see. What I want is the differential equation. So I d this thing is equal to I I'm taking a derivative. So I have to construct this transformation, subtract out the identity part, divide by delta t, and then I get a derivative. I'm putting an I explicit because that is the convention in writing all the quantum mechanics evolution equation. And so now I have to do this. The I part will trivially cancel out when I do. This is one term I here coming on both sides, and that goes away. What remains is, this one is also kind of trivial. It will only produce L mu rho, L mu dagger. And the delta t will go away because of this thing in the denominator. So the only other part comes from the cross term, where one of them will have this factor and the other factor will be identity, and vice versa. So the k is already fixed. K, we have a certain structure which we know what it is, but it will have a term where this h and k is on one side of the row and then it is on the other side of the row, which is the well-known structure which produces commutators. There is a sign difference. So when this is h, the signs will be opposite between the two terms, one in this side and one in this side. When it is k, the sign will be the same on both the sides. And so I will write down the answer because that is what looks in the comfortable form. This I and I all are arranged such that this cancels out. And this is the reason for calling whatever this object is H, because this is exactly Schrodinger's equation. I del rho by del t is a commutator of H with rho. But there is this extra terms, which I have to write down explicitly, and let me not make any sign mistakes. This term is just coming from this part of the product, except that they are on either side of these equations, L mu, and this combination is actually the contribution of k, where k had this summation with a coefficient half, L mu dagger L mu on one side of rho and L mu dagger on the other side of the row. And this is now the generalization to describe a quantum system which is interacting with the environment, and all these operators, L mu, whatever it is, they came from these operations. They describe various type of interactions with the environment. there is a finite number depending on the size of the system, but they can be many things, and this depolarization just happened to be one example, but you can have decay of the excited state, or you can have something which is known as decoherence of the system where the phase information is lost. All those kind of things, they are all various special cases described by this general equation, and it goes under the name called Lindblad master equation. It's the most general structure you can write down, obeying all the constraints of positivity, and on top of this irreversibility, that whatever goes doesn't come back to the system. And it's very useful in making a description of what are called open systems, where some degrees of freedom are the ones you have control over, this rho, and everything else is parameterized in terms of these arbitrary operators, which if you have data, you can try fitting it as unknown parameters. People do all those kind of things. And technically, that is a what you call empirical analysis, that yes, you observe a system behave a particular way. Can you fit it to this kind of a description? If you can do that, then you will have an idea about what are the important operators that interact between the system and its environment. So, yeah, I will stop here. But this is essentially as much as I want to say about all the background which is there in quantum mechanics. Now we'll move on to how to use this machinery to understand computation. And that's a different topic from next class onwards.